Hello everyone and welcome to chapter 2, video number 2 in the 3-phase induction machine course. In this video, we are going to cover the machine terminals and slip-speed concept. Let's start. Let me start the video by this question: what are machine terminal labels? Actually, one of my students asked me this question. We noticed during the lecture you use ABC as a label for the motor terminals or the 3-phase system. But when we visited the lab, we looked for the machine terminals, we found it UVW. Any difference? In electrical power system, we have many labels: ABC, RST, UVW, RYB, and even 1, 2, 3. So actually it depends on the usage and the region they use the label. For example, ABC is used in North America and Europe, some areas in Europe. But usually ABC is used for academic and technical documentation, general purpose motor in academic context. Some textbooks or most of the textbooks, they like to use ABC, and for the power supply lines. Regarding RST, they are used in industrial settings and some IEC conventions. And Japan and Europe adopt this label, RST. Some areas in Europe as well. Regarding UVW, so the industry manufacturers like to use UVW for the motor terminals to distinguish between the motor terminals and supply. And supply could be ABC or 1, 2, 3 in this case, or even line 1, line 2, line 3. A good example for UVW is Siemens company in Germany and IEC standards for motor output terminals. India, Pakistan, and Middle East, in the area beside them, they like to use the color coding red, yellow, blue, which is RYB. Regarding 1, 2, 3, USA, Canada, and some industrial automations, they like to use a numbering system because that one is the schematic and to simplify the labels. And also, numbering system is used for higher phases or higher phase systems. For example, 5-phase machine, rather than to say A, B, C, D, E, you can use 1, 2, 3, 4, 5, and that one make the case symbol. So before we leave these labels, IEC, which is International Electrotechnical Commission standards, they use line 1, line 2, line 3, and motor terminals are UVW, as explained. While NEMA standard, National Electrical Manufacturer Association system, uses still line 1, line 2, line 3, for the line from the supply, but ABC and 1, 2, 3 can be used for them. So here we can use either ABC or UVW. It depends on the machine we are going to use. So we can use any one of them to explain the 3-phase system. I hope that one will be clear now, because when I'm going to explain the machine terminals, I'm going to use ABC, but when we're going to look for the live demo, we're going to find it UVW. So now let us look to induction machine terminals. If you remember from chapter number 1, we looked for the 3-phase winding and how to build 3-phase winding inside the induction machine. So each pole should accommodate all phases. The phase displacement between adjacent phases is 120 degree electrical, and the start and finish of each phase or specific phase is 180 degree electrical. So respective from these conditions, we end up by 6 terminals like what we see here. For phase A, we have A1 and A2, or sometimes we call it A and A dash, it depends. B1 and B2, C1 and C2. So we have 6 terminals, we need to connect them. That one for the squirrel cage. Regarding the slip ring, we have 6 terminals in the stator, like the squirrel cage, but we have another 3 terminals in the rotor, KLM, we call it KLM. Because the rotor is wound as star winding, internally connected, so we can access 3 terminals in the rotor KLM. So we need to connect the machine as a star or delta connection. Let me remind you about the star connection. So the star connection, we have the coil A1 and A2, B1 and B2, C1 and C2. So we need to connect B2, C2, A2 together to make a neutral point. So how we are going to do it? So look for the squirrel cage machine. We are going to connect A2 point by B2 point by C2 point. So we have a neutral point here. And we are going to feed the machine from A1, B1, C1. Regarding the slip ring, we have the same action in the stator. We're going to connect A2, B2, C2 to make a neutral point, and we're going to feed the machine from A1, B1, C1. But we need to connect K and L and M together. We need to short circuit the rotor. Why you want to short circuit the rotor? I'm going to explain that one in details when we are going to cover the theory of operation in the next video. But now, to have the motor action, we need to close the rotor. Another question, can we have the neutral point A1, B1, C1 and feed the motor from A2, B2, C2? Yes, no problem at all. What about the delta connection? Let me remind you by the delta connection. If we have the coil A1 and A2, or AA dash, whatever you like, and B1, B2, C1, C2, if you notice here, the end of A coil, we call it A2, or the finish of the A coil. A1, we call it start point, A2, we call it finish point. So the finish point of the coil A is connected by the start point of coil B. And the finish point of coil B is connected by the start point of coil C. And the end point or finish point of coil C is connected by the start of coil A. How we are going to construct that one for the machine terminal? Let's look here. So the end of coil A is connected by the start of coil B, the end of coil B is connected by the start of coil C, and the end of coil C is going to be connected to A1 point. And then we are going to feed the motor from A1, B1, C1 or A2, B2, C2. It doesn't make any difference. So that one is a square cage one. What about the slip ring? So identical to the stator, are going to have finish connected to end, finish connected to end, finish connected to end, and then you are going to feed the motor. But you need to close K and L and M. You are going to short circuit the rotor here to have this point shorted. That one is similar to the square cage we have end rings. Right, there is no neutral point for the delta connection. Can I make the opposite rather than connecting finish to start, start to finish? Yes, you can connect A1 to B2, B1 to C2, and C1 to A2 and feed the motor from any side. Back to the real machine we had before, we have here the nameplate explain the terminal box connection. If you look here, you find the information that he said that we have a delta connection and the star connection. And the winding here are UVW, U1, V1, W1, U2, V2, W2. But we notice something different from what he explained from the previous slide. It's not like U1, U2. Here we found U1, W2, V1, U2, and W1, V2. For a star connection, it doesn't make any difference because you are going to have a neutral point here, and you are going to feed the motor from line 1, line 2, line 3. But they make this arrangement to make the delta connection more simple. You are going to connect directly U1 to W2, V1 to U2, and W1 to V2, and then you are going to feed the motor from this side. Let me explain that one for you to be more clear here. Rather than the arrangement I did in the previous slide, U1, U2, V1, V2, W1, W2, so they shift the connections here. If you like to have a star connection, so you are going to connect these points together. You make a short circuit, you make a neutral point, so they are going to feed the motor from here, U1, V1, W1. You like to make a delta connection, or what you're going to do, just connect this point by this point, the start of winding U with the finish of winding W. The start of winding V by the finish of winding U. The start of winding W by the finish of winding V, and then you are going to feed the motor from these points. That one will be line 1, line 2, line 3, or we can call it ABC, UVW, whatever you like. So let's go to the real machine and look for the terminal box. But the question now, how do you know that this winding is U1, U2, or W1, W2, or V1, V2? So I need to test that one to know the winding arrangement or the winding, which coil represents UVW. Let us see. We have here the machine, 6 terminals, 1, 2, 3, 4, 5, 6. So we can connect that one as a star or delta. If you like to connect that one as a star, we're going to connect these 3 points together. and that one will be the neutral. I'm going to feed the machine from these 3 points, U, V, W. We're going to take one of these points, take that one away, and then take the wires out connected to the supply. If you like to connect it as a delta, so we are going to connect this point to this point, and start to finish, and feed the machine U, V, W. That one as per the nameplate diagram. I need to make sure that these coils are not the same coil, or these 2 points are not from the same coil. So I'm going to use a multimeter here. I'm going to put it in the buzzer. So if I put the measurements here, that one here and that one there, so that one should give me overload or open circuit, and that one should be open circuit, and that one should be open circuit as well. But if I connect this one to this one, so they are the same phase, so that one will be something like U1, and that one will be U2. And that one will be something like V1, and that one will be V2. And that one is W1, and that one will be W2. So if you like, you can make different arrangements. You can move that one here and make U1, U2 here, V1, V2 here, W1, W2 here. It depends on you, so whatever you like. But now we know what are the terminals, because the coil should have low resistance, and between any 2 coils, we should have open circuit. Let us conclude the machine terminal topic. We looked for the real machine. We have this diagram, so we have 6 terminals. We can connect the machine as we wish, star or delta. But to know the specific coil terminals at the start and finish, we need to use something like the ohm meter. So if we measure between U1 and W2, for example, we're going to have mega ohms or open circuit. Between W1 and V1 will be something like mega ohm or open circuit. But between the start and finish for a specific phase, we are going to measure a certain value. I'm not concerned with the value now, because we are going to look for that one when we are going to cover the machine parameters in the next chapters. But between any of the phases, so we should measure something like mega ohm. But for the specific phase, we should measure a certain value between V1 and V2, between W1 and W2. Also, if we notice that U1, VU2, V1, V2, and W1, W2 should give almost the same value, because the machine is symmetrical. So now we have the option to connect the machine as we wish, but we need to consider the nameplate values, something like the rated voltage and rated frequency, rated current, and how we are going to arrange the terminals. Now let's look for the second part of this video about the slip speed concept. We understand what is the meaning of the word slip, what is the meaning of the word speed, but what is slip speed? To explain that one, we need to look for this example. Assume we have a train is running by a speed V1 km per hour. And in a parallel rail, we have another train is running by V2 km per hour, where V1 is more than V2. What is the speed of this driver? So the speed of the driver is the difference between V1 and V2, delta V equals V1 minus V2. If the second train catches the first train, so the speed of this driver is 0. What is the relation between this example and our induction motor? The 3-phase induction motor has a stator and rotor. The stator has 3-phase winding, and the winding is going to produce a rotating magnetic field running by a synchronous speed Ns, where Ns equals 120 Fs over P, where Fs is supply frequency and P is the number of poles. And there is a rotor running by Nr in RPM. Please note that Ns is more than Nr. Hypothetically, we are going to add a guy between the stator and rotor, and then we are going to ask him, what do you see? He said that above me, I see a rotating field is running by a synchronous speed. And below me, there is a rotor running by Nr speed in RPM. So what about you? He said that I'm slipping by the difference between Ns and Nr, where slip speed equals Ns minus Nr. So we can say that slip speed equals Sns. So what is the slip speed? Slip speed is a portion of synchronous speed that the rotor is lagging behind. And we call it SNS, where S is that operator. So slip operator per unit, unitless ratio or percentage. So we can say that one, which represents how much slower the rotor compared to the stator speed, synchronous speed. So if we're going to arrange that one in per unit or percentage ratio, so we can write that S equals NS minus NR over NS. NS is an RPM, NR an RPM, so S will be unitless. Or we can write it as a percentage or a ratio between the slip speed and the synchronous speed. In the real machine, who does this guy represent? So this guy represents the induced voltage in the rotor bars. Rotor bars or conductors, it depends, square cage or slip ring induction motor, but we are going to use bars for simplicity. So the induced voltage in these rotor bars, E equals BLV, V relative. So the speed, the difference between the stator field speed and the rotor actual speed. So we are going to make a simple proof here. SNS equal NS minus NR. So we are going to substitute by NS equal 120 Fs over P. So S multiplied by 120 Fs over P equal NS minus NR. So SFS equal P over 120 NS minus NR. So that one is a new frequency. We are going to call it FR. So the frequency of the voltage induced in the rotor bars, FR, depends on the difference between the stator field speed and the actual rotor speed. And FR equal SFS. So this frequency depends on the supply frequency by the term S and the difference between NS minus NR. So once you have a voltage induced in these rotor bars, you have a current, and this current is going to produce a rotating magnetic field in the rotor, and this one is going to run by speed corresponding to the frequency of the induced rotor voltage, where FR equal SFS. So the slip term S equals NS minus NR over NS, but we can write it as omega S minus omega R over omega S, where omega S equals 2 pi NS over 60, the angular synchronous speed, or the angular speed for the rotating field. And omega R is the angular rotor speed, equals 2 pi NR over 60. So let's look for the range of S. So S ranges from 0 lower than S lower than 1, and that one is the motor region. Motor region. If S is lower than 0, that one will be the generator action. So the machine is operating as a generator. If S is more than 1, that one is a braking, or what we call it plugging mode. Right. So when S equals 0, so we substitute this equation 0. So this means NR equal NS, and that one, no load condition. There is no induced voltage in the rotor. FR equals 0. But if S equal 1, so this means NR equals 0, the motor at the starting point, and at the starting point, we know that FR equal SFS, so FR equal FS, where S equal 1, and we call the motor at standstill. So the motor is operating in the region at full load, or running speed will be close to the synchronous speed, so that one will be the region where the motor is operating at loading conditions. Let's look in the next slide to explain that one more. Let's look for this example. I simulated one of the machines using MATLAB Simulink. So we are going to speak about simulation later. But now here I simulated this machine at different instances. So for the first one at no load, we have the slip equals 0 and FR equals 0. So this means the induced voltage in the rotor bars is 0 and there is no current in the rotor. If you look for the x-axis, the time, y-axis, the current. So we have a stator current. The machine takes current from the supply, but the rotor has no current. So there is no loading condition. And the frequency of the rotor current, which is the red color, is 0, where FR equals 0. At starting condition, we know that S equal 1, so FR equal SFS, so FR equal FS at this instant. So look here, so the blue waveform and the red waveform, they have almost the same frequency. As you go more in time, you find that the frequency is different because FR equal SFS in the equation. So when we reach the loading conditions, I choose here the full load conditions. I put S equal 4%, or we can say 0.04 We would like to substitute in the equation ns minus nr over ns. So Fr equal 2 hertz, as we can see here. So that one is 2 cycles in 1 second. So one cycle will be 0.5 seconds. So that one is 2 hertz. And the supply is 50 hertz. So the slip term Fr equal SFS. So the machine is running at slip 4%. As you can see here, this is the voltage induced in the rotor, has frequency 2 hertz. And that one in turn give you a current in the rotor. And the current in the stator for this machine is running by 50 hertz supply. Example. Calculate the rotor speed for the following induction motors. Part A. A 4-pole motor fed from a 60 hertz supply operating at 3% slip. Part B. 12-pole motor fed from a 50 hertz supply with rotor induced voltage frequency of 2.5 hertz. So let's start by part A. The number of poles P equal 4 and the supply frequency equals 60 hertz and the slip S equals 3%, so we can write it as 0.03. Please note, most of the students made a mistake here. They write 3% 0.3 and that makes a difference in the values, so 0.03. Right. So we know that the synchronous speed ns equals 120 fs over p. So that one is 120 multiplied by 60 over 4 gives you 1800 rpm. How to calculate the slip? Either you use the equation S equals ns minus nr over ns, or the equation S equals fr over fs. We need nr, we know slip, and we know ns, so we can rearrange this equation as nr equals ns1 minus s. So that one will be 1800 rpm multiplied by 1 minus 0.03 gives you 1746 rpm. Please note that the rotor speed is close to the synchronous speed. And as you load the machine, this difference is going to increase. If the rotor speed is close to the synchronous speed or equal the synchronous speed, the machine is going to no load conditions. Let's go for part B. We have number of poles P equals 12. We have the supply frequency 50 hertz. And we have Fr equals 2.5 hertz. So we can use this equation now where S equals Fr over Fs. So that one will give you 2.5 over 50, 5%. We can write it as 0.05. We need nr, so nr equals ns 1 minus s. But we don't have ns, we can calculate ns equals 120 fs over p. So that 120 multiplied by 50 over 12 gives you 500 rpm. So nr equals 500 multiplied by 1 minus 0.05 gives you 475 rpm. Let us summarize this video. In this video, we introduced the machine terminal labels, and also we introduced the machine terminals, number of terminals. If the machine is a squirrel cage, we have 6 terminals, and if it's slip ring, we have 9 terminals, 6 in the stator and 3 in the rotor. Also, we covered how to connect the machine as a star or delta using both slides and live demo. And we covered, after that one, the slip concept, how to calculate the slip speed and the slip for the machine using these two equations, Fr equal SFS, where Fr is the frequency for the induced voltage in the rotor bars. And S equals Ns minus Nr over Ns, where Ns is a synchronous speed and Nr is the rotor speed. And we know the range of the slip for the motor action is from 0 lower than S lower than 1. So if the motor is operating at synchronous speed, which typically corresponds to no load condition, so this means S equals 0. Or close to 0, this means that the machine is operating close to the no load conditions. But if S equals 1, the rotor speed is 0, and this means that the machine at standstill or the motor at starting conditions. What will I watch in video number 3? Theory of operation and equivalent circuit. See you in the next video.